process of vaporization, those molecules at the surface that have enough kinetic energy to actually break away from the liquid and form a vapor. Remember that there's an intermolecular attraction pulling them down, but if they have enough kinetic energy, they can break free and form a vapor. The larger the surface area, the more molecules at the top, the faster the rate of evaporation. Remember that you literally have to be at the top of a surface in order to escape. If you're buried below, you're not going to vaporize. So if I give more molecules a chance to be at the surface, we'll have a larger rate of evaporation. This distribution of thermal energy shows that molecules that contain or that possess the minimum amount of kinetic energy will escape. So if I begin to warm the solution up, I have more that can escape. The lower the temperature, the lower the rate of evaporation. Makes sense. If I increase the temperature, kinetic energy increases, molecules move faster, they'll evaporate from the surface much more quickly. The opposite of vaporization is condensation, going from a gas back to a liquid. Though some molecules of the vapor lose energy through molecular collisions, we have to generally cool a gas to remove kinetic energy to force them to start sticking together again, to actually form some kind of cohesive attraction to pull them back to the liquid form. That process is known as condensation. So we have two opposite processes, vaporization and condensation. Liquid to gas, and then gas back to a liquid. In an open container, the vapor molecules generally spread out faster than they can condense. That process causes it to evaporate. The net result is our rate of vaporization is greater than the rate of condensation, and we'll see the net loss of the liquid. But if we put a lid on the container, put it in a closed container, and the vapor is not allowed to spread out, that results in an equilibrium where the rate of condensation and vaporization are equal. This is known as a dynamic equilibrium. Again, only occurring if I put a lid on the container where I can trap the gases. We'll see the rate of vaporization equal the rate of condensation. If there's no lid, they evaporate away and will never come back to the liquid form. So that effect, the attractive molecular forces, influences the rate of these two processes. The weaker the attractive forces between the molecules, the more likely they will be in the gaseous form. So the result of a weak intermolecular attraction results in more molecules in the vapor phase and a liquid that evaporates much more quickly. If I have high intermolecular attractions, it's more likely to be in the liquid phase. Liquids that evaporate easily are said to be volatile. Gasoline goes from liquid to gas very quickly at room temperature. It's volatile. Even rubbing alcohol, put it on your skin if you have an owie, and it will evaporate quickly. It's said to be volatile. Motor oil doesn't evaporate very quickly. It is said to be non-volatile. The amount of energy required to vaporize 1 mole of a liquid is known as its heat of vaporization. Here's yet another delta H. To move it from a liquid to a gas, that change of phase. Now remember, when we change phase, it does not change temperature. All of the energy being input is being used to break intermolecular attractions. So going from liquid to a vapor requires energy. It is known as the enthalpy or heat of vaporization. It always requires energy. Endothermic, so the heat of vaporization is positive. Equal but opposite is the condensation. Notice they are equal but opposite signs. Vaporization, condensation, equal but opposite signs. We see values here, and we'll be using these in some calculations. Liquid water, for instance, boils at 100 degrees. The phase change from the liquid to the gaseous or gaseous back to the liquid form takes place at 100 degrees Celsius. It takes 40.7 kilojoules for every 1 mole of water to go from the liquid to the gaseous phase. Delta V kilojoules at the boiling point at 25 degrees. All right, so at room temperature, these are standard values we'll see reported. If we're at the boiling point, these are the numbers we would pull out, so we're just giving it at different temperatures. Rubbing alcohol is quite volatile. It takes less energy. Diethyl ether, even less energy. So again, these are the values. How much energy do I input for 1 mole of that substance to change phase from a liquid to a gas? Remember, going gas back to liquid is an equal but opposite sign. Equal number, opposite sign. I'm going to need my calculator, so I'm going to turn the video off now, ask you to find your calculator as well, and just start up again when ready.